Okay, so we're taking a different angle at convergence of series and indirect way of approaching convergence, meaning that we replace series in a very standard way with another series and examine the convergence of that series. Okay, so it is right there in the theorem, or rather in the definition right here. So we replace a series with its series of absolute values. Okay, so and then examine that new series, which happens to be a series with positive terms or with non-negative terms, and so all of the techniques that we have seen there primarily are almost exclusively apply to those series. So that is the replacement is certainly is helpful, but or it is promising rather. It is the theory that makes it really helpful. It turns out that if that new series converges, then the original one does too. Okay, so we have proven it based on that. Well, we proved it yesterday. So the idea is roughly visible here. Well, rather the idea is on the left. The picture is of how we create that series and how the squeeze appears, or at least something that looks like a squeeze of our sequence to begin with. The sequence is now between the on the top it is the sequence of absolute values, and at the bottom the negative of the series of absolute values. Okay, so that on its own does not prove that there is a convergence, but the way we did it with some clever algebra, we did demonstrate that it is in fact the case. That is the theorem at the top, and as a corollary, we have the new theorem about absolute convergence. Okay, alternative, the term is the descriptive in the sense that the absolute convergence comes from the convergence of the series of absolute values. However, the term that we have to also deal with, it is when series converges but not converges absolutely, that we call it conditionally convergent. Series converges but not absolutely. We say it converges conditionally. Okay, so it is not a common occurrence in a sense, but it does happen. Most of the time we will rely on absolutely convergent sequences. So the examples are of the idea. One is the main example is here, is that we take our alternating p series, created by -1 to the nth power between -1 and 1. So and then we take the absolute value of that. We produce then the series of absolute values, which is simply the p series, 1 over n squared. P is equal to 2. It converges. And then, which means that the original series converges absolutely. So that's a number one step, or rather, in a way, I would say it is number two step. Number one step is divergence test. Just in case, make sure that an converges to 0 to begin with. If it does not, then it diverges and you're done. And number two, try absolute convergence. Meaning that you look at this, okay, and then once again, if it converges, then you're done. Only number three, if it does not work out, if you pass the first step but did not pass the second, so in other words, it does not converge absolutely, then you proceed to the next step and try conditional convergence. Okay, so that's roughly how we do things. Whenever we encounter a specific series, it might be interesting or timely to go back where we started and make sure that that we don't forget where we started. And we started with approximations of functions with Taylor polynomials or power series, generally speaking. So how does it apply to those? Okay, so if so we have power series, which is looks like this. Okay, so it might or might not approximate something. The theory goes with the just take all power series and see how they behave. So that's what a power series looks like. It is Cn is just the coefficients, and this is the center, which might serve as the point of approximation. And then we are interested in convergence of these series. And then it depends on x. So hypothetically, we would have to examine the convergence of this series for every x separately. Okay, so the question becomes: is it possible to do it once and for all for many values of x? And it turns out it is possible, but every time you'd have to look at the absolute value. So because without absolute convergence, it does break into separate values for x, and they have to be examined separately. Fortunately, this is what we look at. My an is equal to Cn x minus an. Okay, so that is if you want to go to connect this power series to the theorem in the definitions. So this is my sequence, and then I go on to look at the sequence of absolute values. So it will be Cn x minus an absolute value, which can be factored out, and we have x minus a to the nth power. Okay. So then this is the series we will be comparing to our original series. So sum Cn x minus a to the nth power. So this one is a truly will determine the behavior of the original function, and it will be able to concentrate on nothing but the coefficients. So the coefficients of the series will determine whether for what values of x we have convergence. It is important to remember that if we look at the original series, it is at the top, so it depends on x, which means that it could be easily could take negative values. Okay, so when n is odd, x is less than a, then that term will be negative. But as x is larger than a, it will become positive. So if you want to deal with all possible values of x, then you cannot rely on the test for series of positive terms. And that is why you do have to make that step. The step that I just made to converting to absolute values is inevitable if we want to treat the whole thing at once. Positive and negative values simultaneously. How? We just attach absolute value, and all of a sudden all the terms are positive, and then we can treat the whole thing at once. The illustration I want to bring up again here is the convergence of, so once again, there's that picture. I think this is the one, yes. Okay, so this is what I have been talking about. Approximation of a function that happens to be 1 over x by a sequence of Taylor polynomials. The red ones are the Taylor polynomials and go up to degree 7. Okay, and that is they are like partial sums of our Taylor series. Okay, but what happens if I attach absolute value? This is what happens. So the picture changes slightly, like this. Okay, so same sequence. So what happens to the absolute value? To the 0 degree, 1 degree linear becomes V-shaped. The parabola is cut, so compare back to here, the third picture from the left. In the middle, it is a parabola, but I'm not sure I'm doing the same exact function, but the idea is here we always have what the absolute value creates. It creates a cusp. It creates a cusp at the at 0. well, so if we are approximating at 0, then at 0 there will be a cusp even when the it becomes less and less visible, but it is there. And then we're looking at the convergence of this sequence of functions, partial sums of the Taylor series, to whatever. We don't care where it converges, as long as it converges. If this one converges, then so does this one, and which means that we have our approximation. Okay, so that's the absolute convergence for us. Okay, this thing doesn't work. Okay, so that simplification works out every time. This one we just have to stop here until we make a full circle and we come back. So this is where we are right now, absolute and conditionally convergent series, and this example is pretty perfect. But we need an example of a conditionally convergent series. So why does it even make sense to bring it up? And here's an example. So we want an example of conditionally convergent series. Like I said, conditional is not very descriptive term. It is, absolute convergence comes from the word absolute value, but then we are kind of switching to the other meaning of the word absolute, and then the opposite of absolute is conditional. So either it is absolute or it is not. There are some conditions there. Okay, so what conditions there? There are really no conditions there. It just converges, but not as strongly as the absolute convergence. That's all. There's really no conditions for us to worry about. All we're saying is that some AN converges. That's what we're looking for. Some absolute value and is not. Okay, so that's the example we're looking for, and turns out there is a very simple example. The one that series we know that it is divergent is 1 over n. The harmonic series is divergent. Okay, so we know that from the integral test, remember? So then how do we create then a series from this series that might be divergent but might be convergent? We make it alternate. And so it will be once again -1n over n. Okay, -1 over n. So the actual value is the magnitude is 1 over n. It goes to 0 slowly, but it not only goes to 0, but it also alternates between the signs. So when you start adding them up, it will not keep climbing. So this is on divergent because you add terms and they're all positive. So the whole thing, the partial sums, will grow and grow and grow, and turns out it grows to infinity. On the left, we're taking the same values, but we keep add, subtract, add, subtract, so it will behave like this. And then turns out this one is convergent. So once again, we had a picture yesterday of that behavior. Nope. Doesn't work. Here it is. Maybe this one. Let's say this one. No. Okay. So the sequence itself is in the first row, the first picture, and you can see how alternation appears. Two series. The first picture, 2 series, and in the second sequences rather, and they are depicted as bars. Why? Because so that it would suggest us that what we're going to do with them, we're going to stack them up and to add. So addition of those values is stacking up those bars, but then the result is at the bottom. Okay, so and then we have 2 sequences. Like I said, one the sequence of partial sums may or may not be converging. The one at the top, which keeps growing, and the other one is not it does not keep growing. It is going up and down, up and down. So in that sense, you can realize that it might be possible for it to converge because it's not going to infinity. So on one hand it is more complicated because it is not positive, and so the behavior is more complex. But in terms of convergence, it might be possible. So the answer is yes. It is convergent. This series is convergent, and which makes it conditionally convergent because if I take the absolute value, I have 1 over n, I have the harmonic series, it diverges. Okay, so that's what we have. There is in fact a whole theorem that explains takes care of this possibility, the alternating series theorem. So we have a sequence AN, and it alternates between positive and negative. So AN is equal to -1 to the n Bn. Bn is larger than or equal to 0. Okay, so that creates alternation, just like in the example we just saw. And then we have alternation, and then the requirement for this series, which is not positive series, which means that it cannot only converge. We are interested in conditional convergence. The restrictions are fairly limited. All we have to do that an plus 1 is less than or equal to an, so the series is decreasing. And number 2, an is going towards 0. Then the original series, the alternating series, converges. So if you want to be specific, you say it's converges. Well, we cannot actually say that it's converges conditional. It could still converge absolutely, but the fact remains it does converge. Okay, so that is the theorem. The proof is, let's see if I have an illustration. So once again, to illustrate why this could be true, maybe I don't have an illustration here. No, I don't have an illustration, but you can imagine what this one is fairly decent illustration of why we're going to be that convergence is possible, because it is squeezed between two series, one positive, one negative, and it will alternate between them like this. The partial sums will be alternating between the two, and ultimately we'll have to converge. Okay, here it is. Okay, so if you want more examples, the theorem provides us with those, starting with 1 way, and every one of these will converge. So I take up P series, and we have a bunch of P series that diverge. 1 over ns, or P rather, diverges when P is larger than, or rather smaller than or equal to 1. Okay, that's a P series. In the meantime, so we have divergence. But if we make from this series, we make a series that is alternating, it will converge. So -1 to the n, NP, it converges. So I have a bunch of examples of such a behavior. But once again, absolute convergence is really what's important. Just keep doing it. Okay, so we're taking our new angle. So alternating series theorem will be helpful sometimes, but it is the absolute convergence is really important. So now we are circling back to positive series now, because now we know that we can actually, it is helpful to consider positive series only, because we can prove convergence of multiple other series. So let's go back to geometric series. which is an is equal to a times r to the n, or recursively an plus 1 is equal to an times r. Okay, so and then we know that the series converges. ARN converges depending on the value of the ratio. Specifically, r between negative 1 and 1, we have convergence. When r is positive, then we have certainly. Well, actually, that's the good thing about geometric series. We have the theorem about geometric series is equally applicable to positive or negative terms, right? So look at the conditions already about the absolute value of r, which determines which is the ratio, and it determines whether or not you have alternation of signs. And when r is negative, you have alternation. When it's positive, there isn't. But the convergence occurs regardless, as long as the absolute value of r is less than 1. Okay, so it's a very convenient series, and the theorem is very, very strong, so we can apply it equally. So how do we apply this idea, utilize it for other series? So non-geometric series, suppose we are facing that. So some Bn, or let's say An. Okay, so what is the analog of the ratio? Okay, so the series is not geometric. What if we try to think about as if it is and find an analog of the ratio? And it is visible here. Okay, so every time, how does it do? We build their geometric series, we multiply by r every time. So in other words, a ratio has a meaning. It is an plus 1 over an. Okay, so that's why it's called the ratio. So if I have also take the ratio, but the series is not geometric anymore. What does it mean? It simply means that that r will depend on n. Like this. That's all. So that's the analog. That's the analog. Rather than having one number, and that's if we're lucky, it is one number, and we have a geometric series, and then we know everything there is to know about that series. So if we try to utilize that idea of ratio, I mean, look at the ratio. After all, what is the meaning of it? It is by how much the series decreases, the sequence decreases every time we progress to the next element, right? So either you take this one or you take that one. It's clear what the ratio does. It shows you how much you progress at every step, and so it's better that step to be bringing the whole thing down in order to ensure convergence. Okay, so that is why we end up with this condition over here. So every time we make the next element should be smaller than the previous. The next element should be smaller than the previous one. Okay, so that's why the ratio has to be less than 1. Yeah. Okay. We can use that idea similarly for non-geometric series. The only problem it is now depends on it. So in effect, we end up with, instead of a number, we end up with a sequence. So it's a sequence. And then we want to have a similar restriction on our series, which is not geometric. And we want to have as definitive answer as with the geometric series, but it depends on it. So it depends on it, but its limit does not. Okay, so limit. So what if that limit exists? So we take R, define it as the limit of an plus 1 over an. And then the hope is that it will supply us with a number that characterize characterizes the series. Okay, so maybe as well as it characterizes the geometric series. So you can still call it the ratio or the limit ratio or whatever you prefer. It is the formula that matters. And then the hope is that restriction right at the top, right here, will be the same. Will be the same. So r is less than 1. Then we have convergence, and indeed it is exactly what our answer is. We'll look at that limit, and these that the value of that number will tell us what the convergence of the series, as long as we stick with the positive term series. Okay, so so that's the theorem. Let me just state the theorem. Well, let me give you an idea of why this is the case. So suppose there is a convergence. So we have a limit of a sequence, which means that it's possible, there's a possibility that it might not exist. Or it might also be a large number, then that will be indication of divergence. It could be infinity as well. But suppose there is a limit. Then, as you can see, if you think about it, so suppose the limit exists, let's assume, then what we have here is a sequence of ratios that converges to this number. Okay, so these are my ratios, an plus 1 over an, and they converge to this value r. Okay, in some manner that is not important really, in what manner it is, but it is interesting what happens if that number r is less than 1. Okay, so then this is 1. This is 1. R is below 1, and our sequence converges to R, which means that eventually, that's the nature of convergence. Eventually, the tail of the sequence, of our sequence of ratios, will be below that level. It will be less than 1. So in other words, you're going to have what? Let me squeeze one more number in between. Let me put it. Let me code r over here. So I'm squeezing number r between r lowercase and 1. Okay. Then what we have here is an plus 1 over an will be less than r capital. Okay, so in other words, we have an plus 1 less than r an. Okay, so that is the fundamental observation that will allow us to demonstrate the convergence of our series, and indeed it is not a challenge at all, because once we're starting, so add these up. So add these. We have the point is that we have this estimate of each element of the next element based on the previous element. As you can see, once again that I try to bring it up about the geometric series. It's still applicable here, but instead of having an exact step every time you just multiply by a certain number that then brings things down. Maybe it does bring things down, but not by an exact amount, but by some amount that is unknown, but at least we have an estimate. So as you can see, there will be r is less than 1, which means that every time we progress to the next step from n plus 1 to an, what happens? We multiply by r capital, which is less than 1, which means that it will be bringing down our sequence at that rate, at the rate of r uppercase. Okay, so and that is behavior which is almost exactly the same as that of a geometric series. And here's how you can discover what this is. What the end result is. It is less than r an. Okay, And now, so if I take this inequality and apply it several times, I'll keep applying it. So so on the second one, I can express for inequality the previous element in terms of the next, rather vice versa. Okay, so I did express an plus 1 in terms of an. Now I'm expressing an in terms of an minus 1. So it will be r times, so I'm looking at this parenthesis. An is less than r an minus 1. Okay? An is less than r times an minus 1. So we are moving backwards. So we're trying to understand what an plus 1 is like, but how we are moving all the way backwards, trying to find the very first element of the sequence in that manner. So, and we keep doing it, r times, so now the next one I concentrate on this. And so I have r squared times, well, what's left there will be r times an minus 2. I went one more step backwards. Okay, and then I keep doing it. I keep doing it at every step. I move backwards. I have an extra appearance of r uppercase. Okay, so then you can guess how many times you're going to have it until you reach the very first element of the sequence, and then it is what is it? N times. So it will be Rn A naught. Okay, so in other words, our sequence, the original sequence that we care about, this one, has been compared to something else, this one, and this one is a geometric progression. Okay, so once again we have a comparison between series, and even though the original series is not geometric, we have compared it to directly compared to geometric series. Okay, and then that's good news. So let me write it out again. So an less than, say, b, or less than or equal to bn, where an is positive. Okay, so that's important. And where bn is a geometric progression with r less than 1. Okay, ratio less than 1, which makes its series convergent. So sum bn is less than infinity. So we are in the, where are we? We are in the position of where we were a couple of days ago. It is the direct comparison test. An, bn. Bn just happens to be the geometric series, convergent, because remember how r was chosen, that r capital was chosen to be less than 1. So we have that series is convergent, and then we have an equality, a direct comparison. So direct comparison has appeared, and the direct comparison test applies to this situation, and so we conclude that sum an also convergent. Okay, so once again, an was not assumed to be geometric, but we compared to geometric series under the assumption right here, that was the big assumption right here, that the limit of ratios exists n less than 1. The limit of ratios exists and less than 1. Okay, then the comparison works out. Otherwise, it does not. Okay, so let me try to put this together. So this is a almost complete proof, but half of the proof of the theorem that is called the ratio test. So here we're referring not to the ratio of the geometric series, but the ratio that we are facing over there, n plus 1 over an. Okay, so we have a series. So suppose an is a series. Okay, we also suppose that we have the sequence of ratios converges. R is equal to the limit of, I'll put absolute value here. Okay, so and then just as it has been a few times, we have several cases, and the main case is when it is less than 1. So case 1, it is less than 1, and the series converges absolutely. And then when it is larger than 1, it diverges. Okay, so as you can see, there is a third case. There's a third and fourth case. Third case is R is equal to 1, test fails, as well as it fails when case 4, if you want to include these, the limit doesn't exist. Once again, test fails. So test fails, meaning that the theorem is not applicable, and then you have to have different methods for solving it. So, so the idea of the theorem is it is a kind of a comparison test, except the actual comparison is hidden. So it's inside of the proof we did comparison of our series with a geometric series. But now it turns out the end result is actually is not about comparison to our series with some specific series, but rather to itself. So we are looking at the ratios of two consecutive elements and see where that. If there's any pattern in that behavior, and the limit exists, less than 1, you have convergence. So here's an example. So what happens when when you try to form this this ratio? You hope some simplification will happen. These simplifications happen especially easily when you have powers and also when you have factorials. So one series that we have talked about already, and that was, remember, the series of the exponential function that we found, 1 over n factorial xn. Okay, so then the question becomes, what about this term? What about this this term? This is my an. So how do we prove convergence of this? So even though previously we have demonstrated this is actually works out based on our Taylor polynomials analysis, we could now apply and see what happens if we apply the ratio test. And that's uncomplicated. We just take an plus 1 over an, and things tend to cancel when you do division. So if you have a formula, explicit formula, where you have powers, you have factorials, things will cancel out. So I'll have my an plus 1 is 1 over n plus 1 factorial xn plus 1, okay, divided, well, let's have the absolute value here, and I have here 1 over n factorial xn, okay, and then I simplify. I split it up. I separate x's from the rest. So I'll have over here I have what is it, n factorial divided by n plus 1 factorial, and here I have xn plus 1 over xn absolute value. Okay, the first simplification is of canceling. So n factorial divided n plus 1 factorial, what does it give us? Remember what factorial is? Factorial is the product of all elements up to n, so it will be 1 times 2 times 3 times n, and in the denominator I have 1 times 2 times 3 times n plus 1. Okay, so the cancellation is very effective. You are simply left with n plus 1. Okay? In the meantime, what happens on the right, it's simply the second term gives me nothing but the absolute value of x. Okay, so what happens is then we're left with absolute value of x divided by n plus 1. What is the limit? What is the limit? So don't let absolute value of x confuse you. It's all about n plus 1. So, I mean, x is just a number. And a constant number. It does not depend on n anymore. So what's the limit?
0.
0. Okay. It is 0 for every single value of x. For every x. So that is my R that we were looking for. This is the limit of the ratios, which you still call the whole thing. The ratio of our series, and its limit is equal to 0. So by the ratio test, the series converges absolutely. The conclusion that we made previously, and that is converges absolutely means converges, and for every x. That's the crucial part, is for every x, because the difficulty when you're facing a power series is not to end up treating every x separately. Turns out it doesn't matter what x is, you have your convergence, which means that the whole function on the left, at the top, the whole function on the left, will be approximated by the series on the right if you truncate, that is. But otherwise, you can say that the left-hand side and the right-hand side are the same function for the whole domain, and the domain is negative infinity, infinity. So you have one function with that domain on the left, and the other one given by a series is on the right. So that replacement that we were thinking about a while ago, about replacing functions with their Taylor series, works out. Because how do you replace one with the other? You replace a function with a series that is convergent. So you cannot replace it with a series, just any series you write it up. Okay, and that might happen. Even though you have Taylor coefficients, all of there is available, but we know that there are circumstances when there is no convergence, or at least there is convergence for some values of x and not for others. So that's what we're gonna watch out for. But at this time, this works out perfectly, because for every x from negative infinity, infinity. So in other words, just as the exponential function is defined on negative infinity, infinity, so is the power series on the right. So the replacement then is perfect. Okay, the example when it does not have to be the case, we just saw this is right. So because of the hole in the domain right here on the x-axis, the x equal 1 is a hole in the domain, then you cannot possibly expect the series to behave the way we just saw, so it converges everywhere, even though you can see how these polynomials are convergent as far as the behavior close to 0 is concerned, but as you get closer to the hole in the domain of the original function right here, you can see what happens. The branches go up and down, and the odd polynomial, it points down, or up rather, and when the second branch appears, so a second branch appears when the degree is odd. 7, 5, 3, there is a second, that branch, what I'm saying is that branch of the second branch of the function is not being approximated anymore. Okay, so let's take another example. So this is, in reality, is what our main interest in this topic is how this applies to to power series, but let me take another look at the series that has no x. It is kind of simpler, and so we'll take a look at it. So series 2n and factorial, and once again, once you've seen it you've seen this over here, this part once, you know that it's going to happen every time. You have powers, you have factorials. These things always cancel out once you form a ratio. Why? Because every time both of them are defined recursively. So the power is what it is. Every time you move on, you multiply by 2. That's what the numerator is. And denominator, as you move on to the next one, you multiply by n. Either way, the rest is gone once you start doing fractions. So an is equal to 2n over n factorial. The ratio would, that's not the ratio right here. The ratio I found is here, R0. Okay, so I go with a fraction n plus 1 over an. Okay, so it will be 2n plus 1 over n factorial divided by 2n plus 1 factorial. Okay, so similar computations altogether. Divide by n factorial, so I have 2n plus 1 over 2n n factorial over n plus 1 factorial, and we are pretty much in the same place. There is a cancellation. I have 2 and I have 1 over n plus 1. Okay, once again I have limit equal to 0. It is exactly the same example as above, except x is variable. Variable is missing, and so we have explicit formula, and 2 divided by n plus 1 gives me 0. So r is equal to 0. So by the ratio test, the series converges absolutely. Well, of course it converges absolute because the series has positive terms in it. Okay, so we have 1 week left, and we'll just hopefully have a time for review.